Okay, so this is the second video for titration curve calculations. If you didn't watch the first one, do that one first. And this one will make a little more sense to you. So we did the first A, B, and C part of this, this problem in the last video. We're going to do D and E in this video. So if you remember, we were looking at the buffer zone of the pH curve. And point D is at the equivalence point. And so for this particular reaction, I've got 0.1 molar acid, I've got 0.1 molar base, and so the equivalence point is when the two volumes are equal. That won't always be the case. And actually, I've drawn that just a little bit low. I'm looking at my pH here, so this one's going to have a little higher pH than that. So let's say our equivalence point is maybe, lost my pen, maybe up here, just a tad, should be above 7. Anyway, this is a much lengthier calculation. Now, you don't have to write all of this out every time. I did it for this one because I want you to understand, you know, where all these numbers are coming from. But you don't have to physically show me all of this work every time you do a problem like this. So here's our titration reaction. The acetic acid reacting with the hydroxide from the sodium hydroxide gives you the acetate ion and water. Now, at the equivalence point, by definition, that means that these two numbers here, after the reaction should be 0. I've got a stoichiometrically equivalent reaction. And in this case, it's 1-to-1. Exactly 0.00250 moles of the acid and 0.00250 moles of the base. And so you don't have to calculate the amount of acid every time. If you remember, we did that in this first part of the problem. And so with the equivalence point, I know if this was the amount of acid, that's also going to be the amount of base. So I didn't do the calculation separately. But the important part here is I don't have any of the weak acid, any of the strong base. So the thing that's going to affect the pH is going to be this conjugate base of this weak acid. So this is a KB problem now. So I went from Ka to buffer to now KB. But there's an extra step or two in this one as well. At this point, I have to start thinking about the total volume, because if I've got a KB problem, I'm dealing with molarity. And so to get to this point, I added 25 milliliters of the acid, 25 milliliters of the base. So this solution here is a total of 50 milliliters, 25 plus 25. And so I've got to use that to find the molarity. So I know how many moles of the acetate ion I have, and I know the volume. So 50 milliliters is 0.0500 liters. So to get molarity, the moles over the liters. When you divide that, you get 0.0500 molarity for your acetate ion. So again, this is a KB problem. I've got a molarity. The only thing I don't have at this point is a KB, but I can find that. So the KB of the acetate ion is the KW divided by the Ka. So this is the Ka from the original problem. That's the Ka for your acetic acid. So when you divide that, you get 5.6 times 10 to the negative 10. So now I've got everything that I need to solve this problem. So the actual reaction that I'm doing at this point, the KB reaction, looks like this. The acetate ion is going to react with water. It's going to form an equilibrium solution, and it's going to give me a little bit of the conjugate acid and hydroxide. Not to the point that we're going to have a buffer system here. I'm going to get a very, very small amount of this. So I've just set this up just like we did the Ka before, except this is a KB. So there's my KB, 5.6 times 10 to the negative 10 equals x squared, x times x for my products, over 0.050. I'm ignoring that x to make the math easier. So multiply 3 by 0.05, take the square root of it to get your x. And so x here is 5.29 times 10 to the negative 6. Much, much less than this. I don't have to worry about that 5% rule. The other thing to remember at this point is that this is a hydroxide concentration. This is not hydrogen. So to find the pH, there's more than one way to do this. I think the easiest thing is just go ahead and find the pOH. So negative log of that concentration to get a pOH of 5.28, and then subtract that from 14 to get a pH of 8.72. Again, a basic pH. That's what you would expect from this reaction. This is probably the most involved calculation of the ones that we're doing. Now, last thing. Part E of that question. What's the pH after you've added 35 milliliters of the base? So we know we're going to be up here in a basic solution at 35 milliliters. We have excess of that strong base. So again, one of the big keys, like I said before, is think about what's in the beaker. And that's what this BCA chart is going to show you. The BCA charts are telling you what's going on in the titration reaction. So I've got that same 0.00250 moles of acetic acid that I started with. That doesn't change all the way through the beginning. But now I have 0.00350 moles of the base. To get that, it's 1 mole per liter, 0.1 mole per liter, sorry. So there's your molarity times the volume, liters cancel out, and that's where I get this number of moles. So 0.00250, 0.00350. Now the acid is your limiting reactant. So my change line, I'm going to subtract that amount for both of those, add that amount over here. Remember, the change line always has to be in ratio with your coefficients. This one's 1 to 1 to 1 to 1. So subtracting here, I've got strong base left over, 0.00100. I do have some of the weak base that's present, and of course the water doesn't affect the pH much, that little amount there. For this one, again, I have to consider the total volume. So at any point past your buffer zone, take the volume into consideration. So my volume here, I've got 25 milliliters of the acid that I started with, plus 35 milliliters of the base. That's 60 total milliliters of solution. So my molarity, I'm going to look at that strong base first. It's 0.001 mole over 0.060 liters, which is 0.0167 molarity. I've just divided that by that to get this number here. So this number is your hydroxide ion concentration. And that's going to give you the pOH. Now, if you're also thinking about this giving you some hydroxide, it will, but just as a point of reference, if I'm on the right page here, look back to part D. When I had just the base, I got 0.0000529 moles or molarity in the OH minus, 5 zeros in front of it. With this one, I've got 0.0. The other zeros aren't going to affect this at all. And on top of that, because you've got this hydroxide already present, the equilibrium that you're going to have from this is actually shifted back toward the product. So the hydroxide that you're getting from the weak base is not going to have an impact on your pH. So you don't have to worry about that in the calculation. You're just going to take this hydroxide ion concentration, find a pOH, negative log of 0.0167 is 1.78, subtract that from 14 to get your pH of 12.22. So all of these calculations pretty much follow this pattern. It just takes a little practice, and like I said to you before, and I'll say it over and over and over as we go through this, the biggest thing here is think about what's happening inside that beaker. You have to think about the reaction or the reactions that are taking place. So as you go through this, again, to break it down maybe and summarize, you have a Ka problem here. You have a buffer problem from here to here. You have a Kb problem here. And then beyond that, it's just a strong base. You can also have the opposite. If you have a weak base being titrated with a strong acid, your titration curve is going to look a little different. So in this case, this would be volume of acid added. In that case, you'd have a Kb problem to begin with. You still have a buffer zone here. At this midpoint, you still have pH equal to pKa. Now, notice this is pKa, and when you do Henderson-Hasselbalch, it's always in terms of pKa. So you do have that extra step of changing that Kb to a Ka and then finding pKa. So just kind of keep that in mind. So you've got your buffer zone here. At the midpoint, again, only at the midpoint this is true. Then at your equivalence point, if we start with a Kb problem, this is going to be a Ka problem. And then beyond that, you're going to have excess acid. So it's the same process. You're just looking at bases versus acids. And so you have to think about if you're looking at an OH minus or an H plus concentration. It's reversed with that. So that's about all the time we have for this video. You're going to work on a few practice problems. Don't get discouraged. This just takes some practice, and we'll do some more in another video tomorrow with some more practice. So for today, we're going to look at Kas. Tomorrow we'll look more at Kbs. I'll show you some of these, and then just practice, practice, practice. So I hope this is helpful for you, and I will be talking to you soon.